Okay, I don't care that much. All right. Now you also have to consider the atmospheric pressure when we're calculating this pressure at a particular point. So down here, we have the weight of this fluid, and the weight of that fluid provides a pressure equal to rho times G times H, right? That's where the pressure just due to this fluid is equal to rho times G times H. But you also have an additional pressure up here, which I'm going to call P naught, which is the atmospheric pressure pushing down on the top of the surface of the liquid. So I get a pressure in addition to the total pressure at that point will equal to P naught plus rho times G times H. So that's going to be our expression for the pressure, which is the atmospheric pressure plus whatever contribution you have due to the liquid that sits on top of your point. Alrighty? May I go down from here? Okay, let's try this question. All right, we'll do about 15 more seconds. Now at 1:55, 1:55. It's 5 more seconds. Just guess if you're not sure. Okay, good. A is right. You could probably reason this out because we just said that at 10 meters I have 1 atmosphere. So if I just go to 9 out of 10 meters, then I must get 0.9 atmospheres. And then when you add in the extra atmosphere that you have on the top, that gives you 1.9 atmospheres. If you really want to be rigorous about it there, you would say P, that's P at this point, is equal to P naught plus rho times G times H. You have to convert to SI units. If ever you're in doubt, convert to SI units. So P naught is 1 times 10 to the 5th pascals, plus rho, which is 1,000. That's on a table in your equation sheet, times G, which is 10 meters per second squared, times H, which was 9 meters. And if you do that, you get 100,000 plus 90,000, you get 190,000 newtons per square meter, which is 1.9 atmospheres. An atmosphere is 100,000 newtons per square meter. So that's the way to be more rigorous about it. But as I said, you can remember that at 10 meters, I have 1 atmosphere. So at 9 out of 10 meters, I have 0.9 atmospheres. But then you have to include also the pressure due to the air above this that is pushing down with 1 times 10 to the 5th newtons per square meter, or pascals. Okay, just beware too that you do have these tables in your equation sheet, that you will be using those for various reasons to find the Young's modulus, the density, the specific heat, and other things. So you might have values that aren't given in the problem that'll be listed on your equation sheet. So you just need to be aware that those things are on the equation sheet. And as you practice these various problems, you'll get more accustomed to using them. All right, let's look at Pascal's principle. Although before we do that, I just want to ask a question. This is not sort of related to the class, but not really. And I want you to answer with a clicker. We're revising the state's high school or K-12 science content standards for the state of Louisiana. And this is the first time it's been done in 2 decades. And we're one of the last states to do it too, unfortunately. But we're trying to figure out what should be in the physics class for high school students. And if you've taken physics, whether at a private or a public school, if you haven't taken physics, then don't answer at all. But if you've taken physics, I want you to answer A, yes, or B, no. Just tell me if you covered these topics in your high school physics class. The first one will be kinematics. Did you cover kinematics in your high school physics class? That is the motion of objects, the x is v naught t, all that jazz. Did you cover that in your high school physics class? All right, just a few more seconds. I'll stop at 25. Okay, second, did you cover momentum? Those are the collisions, the F equals delta P over delta T. Did you cover momentum? I'm assuming you covered Newton's laws if you covered kinematics. Did you cover momentum? We'll stop at 15. 15. All right, third, did you cover energy? Did you do conservation of energy? Did you do work? Those sorts of things. Work and energy. Did you cover work and energy? Good. All right, just a few more seconds. I'll stop at 10. 4. Did you cover rotation? Yes or no? That's, theta, omega, alpha, that jazz. All right, so a few more seconds. Most of you have not done that. I'll stop at 15. And then, did you cover fluids? The stuff we're doing now. Okay, about half and half. Let's stop at 12. I won't count this towards your clicker, so don't sweat it. And then 6, did you cover electricity? Cover electricity at all? Voltage, current? All right, we'll stop at 10. Okay, awesome. Thank y'all. All right, so let's look at Pascal's principle. Pascal's principle says that a change in pressure is felt at every point in a fluid, in an incompressible fluid, excuse me. You know what a piston is? Piston's a cylinder. It's kind of like a French press. You know what a French press is? The coffee maker, you push the thing down. That's a piston. Except in a piston, you don't have a screen where you have on a French press. You have, a solid thing. In your engine, you have a piston where you compress the gas and the fuel mixture in your engine. So this is a cross section of a piston, and I'm applying a force per unit area on the top of this piston. So I apply a force in this direction, and because I have an area on this piston, my pressure that I'm applying there is equal to my force per unit area. Now, this pressure is going to be felt everywhere. So I will have a pressure that is felt here, a force per unit area that's felt there, a pressure that's felt here, a pressure that's felt here. It is felt all the way throughout, and in every point within this fluid that is an incompressible fluid, I'll have that pressure throughout. We feel this too with solids. Solids are incompressible. So like for example, if I were to take this and put it up next to my head, and then somebody took a hammer and they applied a pressure to this end, would I feel that?
Yes.
Yeah, the same is true. Yeah, that's not very nice. But the same is true for incompressible fluid. That if I apply pressure to one end of that fluid, then I feel that pressure all the way throughout. So pressures are fluids, incompressible fluids and solids are similar in that way. All right. Now we can use this in hydraulic lifts. Let's see. Let me go to the next page. Okay, yeah. So this principle is what allows for hydraulic lifts. And primarily, this is what we'll be looking at for Pascal's principle. For example, in this case, the input pressure is equal to the output pressure. So if I put in a pressure here, if I put in some pressure P1, that pressure is felt all the way throughout this system at every point, including that pressure is felt over here. So whatever pressure I put in over here, I'm going to feel throughout the entire system. I will feel that same pressure because that fluid is incompressible. So Pn is equal to P out by Pascal's principle. Whatever pressure I exert at one point, I will feel all the way throughout that fluid. My pressure, in this case, is going to be F1 over A1, and that's going to equal to F2 over A2. Now notice that I can solve here for F2. F2 will equal to F1 times A2 over A1. Now let's think about these areas and what that says about the forces. If A2 is bigger than A1, what is my output force going to be? If I have an area here that's bigger than the area over here, how will the force that I've output here compare to the force that I put in? Will it be bigger, smaller, or the same? It's going to be bigger. I mean, you can see from the picture, right? It's a hydraulic lift. That I put in a little bitty force over here, and I get out a big force over here. And so you're probably wondering that doesn't really seem right, because I'm putting in a small force, but I get out a big force. And it seems like that should violate some thing that we've talked about, like the conservation of energy. Because we say that we can't just produce energy. So what's happening here that allows for this greater output force? Have you ever used a hydraulic lift? You have, right? I mean, if you have a jack on your car, sometimes your jacks in your car, they work by a screw type mechanism, but a lot of them are hydraulic lifts. What do you have to do if you have like a little floor jack or some other type of hydraulic jack? You ever tried to jack up your car? You move your car right this much distance, but how far do you move that handle?
A lot.
You gotta sit there and you gotta pump the handle up and down and up and down and up and down a bunch of times. So the difference then is the distance for the input piston is greater than for the output. And remember, the input piston has a small force, but the distance is greater than for the output. So on one side, we have a small force and a big distance, and then on the other side, we have a big force and a small distance. On the side where we're actually pumping the handle on our hydraulic jack, we move it over a very large distance, but with just a small force. And then on the other side, it's actually lifting the car, or whatever it is that you're trying to lift. You get a big force, but only a small distance. So we're still doing the same amount of work. We're just interchanging between the force over which the force that we're using and the distance over which it's being applied. Let's look at pressure measurements, and then we'll do a few clicker questions. You might have seen a manometer or a barometer before. You should have seen possibly in your chemistry class, but we'll see them again here. A manometer is a device that compares one pressure to another known pressure. And so, for example, here I have a closed tube. It has some liquid inside of the tube. On this side, I know this pressure. So this is my known pressure. And then this is my unknown. It's the thing that I want to measure. And I want to figure out some way to calculate then what is the pressure that I want to measure. Well, notice that I have this column of liquid. That's a height h. The pressure due to this column of liquid is equal to rho gh. By the same argument that we made before, that you're walking around with this column of liquid sitting on top of you, and it has a pressure that's pushing down rho gh. And so then, it shouldn't be a big leap for us to think that the pressure here is equal to P naught plus rho times g times h. We're going to throw a little kink into it, though, because sometimes it's positive and sometimes it's negative. And in each case, you want to think about how is the pressure compared to P naught. And so here, how does P compare to P naught? Is P, the pressure P that you want to measure right here, is it bigger, smaller, or the same as P naught? Let's do it as a clicker question. So is P bigger than P naught? Is P less than P naught? Or is P equal to P naught? When you see this on the test, you'll have to ask yourself that question, and then that'll tell you whether to use the plus or the minus here when you actually calculate what P is. So here, is P bigger than P naught? Is it less than P naught? Or is it equal to P naught? All right, let's stop at 40. Okay, good. P is less than P naught. Because if P was greater than P naught, I would have forced all of this liquid into this bubble, as the person might say. All right, this might make more sense if you think of it as a tube that looks like this. Here, I would have P over here and P naught over here. So this would be P, and then this would be P naught. And if this pressure is smaller, then it's going to look like this. If P is bigger, it's going to look the opposite. If this pressure is bigger, they're going to shift in the opposite direction. So if this pressure is bigger than P naught, it pushes the levels of the fluid the opposite direction. If they're the same, how do the levels of the fluid compare? They're going to be level with one another. If those two pressures are exactly the same, they'll be level with one another. So in this figure, P is less than P naught. And if they were equal, the fluids would look like this, where they would have the same height of the fluid. Let's just do a calculation on that, just as an example. So let's say that I have a manometer, I have, I don't know, let's say I have mercury inside of it. That's often used in barometers or manometers. We'll say that this is P naught over here. P naught we'll say is 1 atmosphere. And over here I have P. And let's say that the distance between here and here is 2 centimeters. So I have a difference in the height of the liquid by 2 centimeters. And I want to know what is P. I have mercury in this tube, and I want to know what is P. Well, the first thing I want to ask myself is, my equation is P naught plus or minus rho GH. So the first thing I ask myself, am I going to use the plus or am I going to use the minus? Which am I going to use here, the plus or the minus? Well, ask yourself, is P bigger or is it smaller than P naught? Which is it, bigger or smaller? Bigger. This is bigger because it's like it's pushing down more and forcing the liquid up on this side. So P is bigger than P naught. So am I going to use the plus or the minus here? If P is bigger than P naught, I use the plus or the minus? The plus, because that would make this value bigger than this value. I'm adding that extra to it. So I'm just going to get rid of the little minus there. And I'm going to remember that it's plus rho GH. P naught is 1 atmosphere, but that's not in SI units. What is it in SI? 1 times 10 to the 5th. Pascals, or newtons per square meter, plus the density. Now, that wouldn't be given in the problem. You'd have to look in your table. Everybody know the density of mercury right off the top of your head? It's pretty dense. It's like 13,600, I think. 13,600 kilograms per cubic meter. And then the acceleration due to gravity is 10. And then H is 2 centimeters, but don't forget to convert that into meters, 0.02 meters. And then that works out to be whatever it is. You get 103,000-ish. All right. You'll have a problem with a barometer or a manometer. I'll show you how the barometer works. But you'll definitely have a problem like that. There's some in the homework. There's some on the old test. And we'll work through some in class too. All right. Barometer works exactly the same, except that the known pressure is equal to 0. And so before, where we had P equals rho naught, or P naught plus or minus rho GH, this works exactly the same, except now P naught is 0, and so P will equal to rho times G times H. So here, this is a vacuum. And just like the straw, when you're trying to drink your lemonade at Cane's or whatever, when you create a low pressure here, this pressure will force the liquid up into this tube. And so, for example, if I wanted to know the pressure at 1 atmosphere, or rather the height at 1 atmosphere, let's say that P is equal to 1 atmosphere. And let's say that I have, let's see if I do this. Let's say that we're going to do a couple things. So let's say that I use mercury. The density of mercury is 13,600 kilograms per cubic meter. And I want to know what is H. So P is equal to rho GH. That's 1 times 10 to the 5th is equal to 13,600 times G, which is 10, times H. And solving that, then you get this common number that we see, which is 760 millimeters, or 0.76 meters. All right, y'all heard that number before, 760 millimeters? is what we use to represent an atmosphere. In fact, that is one of the pressures that one of the units for pressure that we see sometimes, which is in millimeters of mercury. In fact, some of you who are in the medical field, many of you already know this actually, that you often measure your blood pressure in those units too, right? Am I right about that? Yeah, that you measure your blood pressure because they do a little thing, you see the little thing of mercury go up. It's the same idea here, that we're comparing one pressure to another pressure, or comparing a pressure to the height of the column of mercury that we're observing. Now, what if this was instead water? What would it be? So I want you to take a moment and calculate what is H at 1 atmosphere. What is H at 1 atmosphere for water? Remember, the density of water is 1,000. So what is the height of this column at 1 atmosphere for water? Doing the exact same thing here, except using a different density. What is the height of a column of water at 1 atmosphere? What is it? 10 meters. Right, so if you were to build a barometer, then the height at 1 atmosphere would be equal to 10 meters. This is going to be 1,000 kilograms per cubic meters. G is 10, and then you solve for H. And H then is equal to 10 meters. That means that if you have a vacuum in your tube, if this has a 0 pressure, P equals 0, then this pressure of 1 atmosphere will push that liquid up all the way up to 10 meters. And that is your theoretical limit for the length of a straw. That if anybody ever tries to get you to drink out of a straw that's longer than 10 meters, say, no way, I don't want anything to do with that. All right? Because you won't be able to do it. In fact, it'll just suck the brains right out of your head. Okay, let's try. There's a video here we'll watch. It's just a few minutes. Well, it's more than a few minutes long, but we'll just watch a few minutes of it since we're almost done.